Hi guys, here we go, heading into our notes on optimization problems. So everything we've done in calculus and a lot of what we did in functions and almost all of math in high school really is building us up to this. Now we can actually optimize things, look at actual real world problems and use calculus to find the best solution. Now, optimization means, again, to find the best solution, and problems means, yeah, you're going to have problems when you're solving these questions, okay? This isn't going to be easy, but I believe you have the tools to do these questions, and the feeling of satisfaction and just pure joy when you're done, believe me, it's worth the struggle. So let's work on these 3 examples together. They're going to give you a baseline for what you need to do. But really, I'll be honest, when you get to the textbook questions, they are going to be difficult. And there's no way for me to do a certain amount of examples to show you every type of trick in the book. So you are going to have to think critically, be resourceful, and just get that grit, okay? And get that feeling of not giving up. So I want you to come to the next class prepared for that. But let's just talk about what optimization problems are. So let's say I could ask you, for instance, to make the minimize the cost of chairs. Okay, you're making chairs and tables, and I want you to minimize the cost. Well, that's not clear because, like, do you want me to make the most that I can, or with the least amount of material, or are you trying to minimize production costs? Like, you have to be specific. So that's where restrictions come in. So we're going to say, like, for instance, given a certain amount of material, what's the most chairs you can make, or what for the least cost, things like that. So that's where your extreme values algorithm comes in, because in all of these questions, you will be given a set of restrictions. So basically, then you'll go through the same process. You'll find a function, you'll find its derivative, you'll set it equal to 0, and then you'll see if solve for that, and then see if that gives you your extreme value or if the endpoints on the intervals do. So I will say before I start, it is extremely, extremely important for you to always place restrictions after you create your function. In advanced functions, I wasn't as picky with that, but as a calculus solution, it is part of your solution to include those restrictions so you know what to test. And it also shows your critical thinking and ability to understand the problem being asked. So this procedure is called optimization. This means to find the best case scenario within a set of restrictions. So again, we have to restrict the domain, and this is included as part of your solution. All right, so applications example. Oh man, we got area, profit, cost, volume, production, distance, but really, like, this goes on and on and on, as you will see in the next few days. So this is one of these typical questions that we have gotten since grade 10. Okay, a farmer has 800 meters of fencing, and to create a field where one side is bordered by the road. So what is the maximum area they can create? Okay, classic question in high school math, right? So here we have the road, and we have this 3-sided fence, okay? So we have 800 meters of fencing. So let's let X represent the width. So that means this would be X, and this would be X. So this remaining distance would be 800 minus 2X. Okay, so we'll say let X represent the width of the fence in meters. Okay, so then we can create a function. So notice that it wants us to determine the maximum area. So that means you need an area function which you maximize. Okay, so be careful to look at what they're actually asking you to maximize. That will tell you the function. So them asking you to find maximum area means you need to find an area function. So our area then is X times 800 minus 2X. Now here's where it's different. Again, you have to put your domain. So our domain here is from 0 to 400. Okay, notice I do not include 0 and 400 because in either of these cases you will have no area and there ain't no fence. So there's no inclusion here, so we actually don't have to test the area at 0 and 400, but this is part of your solution. Okay, this needs to be part of your function or else you will lose major marks. Okay, so we can expand this if we want, minus 2x squared plus 800x. But we don't have to do all of that work. We can just find the derivative. Okay, minus 4x plus 800 and set it equal to 0. So set a prime at x equal to 0. Just move this down a bit. Okay, so we get minus 4x plus 800 equals 0. You rearrange and you get x equals 200. Okay, so therefore the max area is area at, because it says determine the maximum area. So we have to find the area at 200. You put that in and you get 80,000 square meters squared. Okay, why does this work? Because this is just a quadratic function which relates the width to the area. So the maximum is going to occur when the slope of the tangent is 0. You have a horizontal tangent because that's when it turns back down. And so that's why doing this calculus works. Okay. All right, so now we get this dreaded box question. I think you remember it from advanced functions. We had to do a long amount of factoring to solve this problem, and now we can use our calculus knowledge to make it, hopefully, you'll agree with me, a bit more simple. So we have this piece of metal that's 60 by 30. Okay, it's being used to make a rectangular box with no lid. So we're going to be cutting out these squares, which we'll call x. They're all like the same size. So we'll say let x represent the height of box in meters. Oh, sorry, in centimeters in this case. Okay, so our volume then at x is going to be the length. So that's 60 minus 2x times the width, 30 minus 2x, times the height, which is x, okay? 2x again is because you're cutting out an x here and an x here, so you're subtracting 2 x's from each side, and same thing here with the 60. That was explained in more detail last unit, so that's why I'm kind of just going through that a bit quickly. So if you expand this and collect like terms, you get 4x cubed minus 180x squared plus 1800x. Okay, so now we want this to be at a maximum volume. So we're going to take the volume function and find its derivative. So 12x squared minus 360x plus 800. So now, 1800. So now we can set this function equal to 0. So we're going to always say, oh, what did I forget to do? I forgot to put the restrictions here. Okay, you always got to do that, guys. So the restrictions are between 0 and 15. Ooh, got to do that or else you lose marks. Okay, how do I know 15? Where does the 15 come from? Well, if I have 15 centimeters, then this length would go away. I would have no length there. So that's the highest it could be, is just below 15. Okay, so I can't include 15. So again, on my algorithm, I don't actually have to calculate the volume there because it's not possible. So now you're going to tell me that you're setting the derivative equal to 0. So this long function, actually it's not long, it's just a quadratic. But see, now this is great because you just get to solve this quadratic instead of a cubic like before. So notice that everything is actually divisible by 12. So you can make this x squared minus 30x plus 150 equals 0. And then you can either factor, actually it's not factorable, you got to use quadratic formula. So use quadratic formula, and you get x equals 23.7 or x equals 6.3. So you know right away that this is inadmissible based on your interval of admissibility. So this is our answer here, is that our height is going to be 6.3. So it asks for the dimensions that give the largest volume. So notice that in the last question it asked for the maximum area. In this question it says what are the dimensions that give the maximum volume. So you make sure you answer the question as given. So this is 6.3 centimeters for the height. The length then would be 47.4 centimeters, and the width would be 17.4 centimeters. Again, just putting that height of 6.3 back into the 60 minus 2x, and for width, the 30 minus 2x. So there you go. Those are the dimensions that give the maximum volume within the set of conditions. Okay, here we go. This is a kind of a difficult one. Okay, so at any point, I would love it if you guys would really take this example seriously and pause and try to think through as much of it on your own as possible, okay? It is going to be very important that you understand this example. I cannot stress that enough. Okay, we're going to use Pythagorean theorem in here. We're going to use distance, speed, and time in here. We're going to use the chain rule in here. It's going to be a lot of fun. So first, you got to wrap your head around the problem. Before you stress out about the calculus and everything, you just got to really understand, get a kind of a real good context of what's actually happening. So we have Ian's house, and it's right directly north of Ada's house. Okay, so we're going to represent Ada's house with just an A, and Ian is up here. So we are saying that that is 20 kilometers apart from here to here. Okay, leave some space, you'll see why in a minute. Okay, so that's 20 kilometers. So at 9 o'clock, Ian leaves his house and he's jogging south. Okay, so he's going this way. And he's jogging at 8 kilometers an hour. And Ada, she's going this way. They're over here actually. And she's jogging at 6 kilometers an hour. Come on, pick up the pace, Ada. And they're both running for 2.5 hours. So when are they closest together? So think about what this actually looks like. At the beginning, we know that they're 20 kilometers apart because Ian's starting from here and Ada is starting from her house. Okay, and we know that, I mean, if we think about this, we could think, okay, he's going for 2.5 hours. So 2 hours at 8 kilometers is 16 kilometers, and then another 4. So he's going to be going 20 kilometers. So he's actually ending up at her house, and she is going to be going 6 kilometers for 2.5 hours. So 6 plus 12 plus 3. So she's going to be 15 kilometers this way. So they're going to start 20 kilometers away from each other, and they're going to end 15 kilometers away from each other. But at some point in between, they're going to be the closest together because of this hypotenuse that's being created. So imagine if Ian's here just after like a few minutes and Ada's here, then their distance apart from each other is the length of that hypotenuse. And as Ian goes along here, Ada's moving along here. So it's creating this hypotenuse at all these different lengths of time. So the very first hypotenuse, you know, it's very, very steep. And then way later on, it's going to be very, very shallow. But at some point, Ian's distance from Ada is going to be at a minimum. So this distance between them will be at a minimum. And that is what the question is asking us to find. This distance. Okay? So first, you got to wrap your head around that. So if you don't get that, pause and try to figure out this diagram first. Okay? Notice that it says, when are Ada and Ian closest together? So when are they closest together? So they want us to minimize distance. That's the first thing you got to realize. You got to minimize distance, and then you got to find the time at which that's true. So the function that we need to create is a d at t function. Okay, you don't need to write this big if you don't want to. But this is so important that you understand this first. They want us to minimize distance, which means we need to find the derivative of a distance function with respect to time. So if you can figure this out, that is like a huge step. Okay, just realizing, okay, they want us to minimize distance, so we need a distance function. I'm speaking too fast. Okay, so how do we represent the length of this distance with respect to time? That is our next question. And once we find the function, honestly, the calculus isn't too bad. It's getting this function. Okay, so let's first think about this. This is a hypotenuse of this right angle triangle. Okay, so we know that the distance, the length of D, is the square root of Ada's distance squared, okay, because that's how long this is going to be, how long she's gone for. But then Ian's distance is here. So how do we represent this part of the triangle? Well, we know that this whole length is 20. So this part of it is going to be 20 minus Ian's distance. Okay, so this is just the Pythagorean theorem. Okay, rearranged. So again, this length is just how long Ada's been running, and this length is 20 minus how long Ian's been running. Okay, so now we need to figure out how do we represent each of their distances with respect to time, because we want this distance function to be with respect to time. So remember, distance is speed times time. So Ada's distance is just her speed, 6 times the time, how many hours she's been running. And Ian's distance then is just 8 times the time he's been running. So now we have all the information we need to create a function. So we're going to say let d at t represent distance between runners in kilometers in t hours, I think since 9 o'clock, is that what it is? Yeah, since 9 a.m. Okay, so now we're just going to sub in what we know. So d at t is the square root of, okay, Ada's distance, which is 6t all squared, plus that other little section, which is 20 minus Ian's distance, which is 8t all squared. Okay, so this is just Pythagorean theorem, where we have the two distances. Okay, so now that we have the function, now we just think of our algorithm. And this is between 0 and 2.5. So because they run for 2.5 hours, because apparently they have nothing better to do. I don't know. Anyways, okay, so now we just need to find the derivative and set it equal to 0. Yay! Isn't it fun when derivatives become the easy part? Okay, so we bring down this half. And okay, when you expand this, sorry, I skipped the part where I expand this. When you expand all this, it just becomes 100 t squared minus 320t plus 400. So that's just this expanded and collected. Okay, and then that's to the minus a half, and then don't forget chain rule. Now we got to do 200t minus 320, right? The derivative of the inside. Okay, so this looks really brutal, but you'll see why it's not too bad in a second. So you get 200t minus 320 over 2 long root 100 t squared minus 320t plus 400. But don't despair, because now we're setting this equal to 0, and the whole denominator just goes away. So we're going to set d prime at t equal to 0. I'll do it over here. So that actually is just 200t minus 320 equals 0. Because you could put the denominator there if you wanted, but then you just cross multiply and it goes away. So you just get t equals 1.6. Okay, so if you turn this into time, you'll find that's 1 hour and 36 minutes. So you find d at, well, first you find d at 0, which you get to be 20, which we talked about, and d at 2.5, which you get to be 15, but then their distance at 1.6 is equal to 12. So the closest they get is 12 kilometers away. So 1.6 in terms of time is 10:36. So at 10:36, they are the closest together, which is 12 kilometers apart. Fun! I love that question. Okay, if you have any problems with that, please ask me in class. Maybe there are a few things I went too fast with, like the Pythagorean theorem part. Maybe you didn't get where that came from. For sure, please ask me because this is really crucial. I can go slower or whatever you guys need from me, okay? So just to recap our algorithm here, I'm just going to say it verbally for you guys. So the first thing is to understand the problem, identify quantities that can vary, and determine a function in one variable that can be optimized. Okay, make sure it's in one variable. Then you can draw a diagram if you would like. Then determine the domain. That's step 3. Determine the domain. Okay, the restricted domain. You have to do that. And then you use your algorithm for extreme values to find the max and the min. And you use your result to make sure you answer the original problem. Okay, make sure that if they ask you for the volume, you give them the volume. If they ask for the dimensions, you give the dimensions, and then you're good to go. So thanks for watching, guys. I hope you learned lots. I hope you had a little fun too.